I lied. I'm making another video essay. Send help. Anyways, here's a cool algorithm I use to make my dice calculator. This is my dice calculator. The body is 3D printed, it's got hot swappable key switches, you can customize the screen color, save formulas to memory, but most importantly, it calculates dice rolls for me. Look, I love D&D and nothing beats rolling physical dice, but if I have to add up 8d6 manually one more time, I'm going to cast True Resurrection on Gary Gygax just so I can strangle him to death again, damn you, Gary Gygax. I made 2 of these actually. One of them was a gift to one of my DMs who's been running a game for several years now. DMing is hard work, so show them appreciation once in a while. Anyways, this is the first of 2 dice calculators. This was the prototype that made the other one possible. The print's not as good as the final version, and I haven't glued down some of the parts. It's controlled by an Arduino Nano ESP32. The main program loop stores the calculator's state and waits for a key press. Once it detects a key press, it selects from the key entered to determine how to update the state, such as determining if the screen needs to be updated or if an animation needs to be played, or if it needs to switch to a new mode, etc. And now, welcome to Script Kiddie Corner. I want to use gaffer's tape. Gaffer's tape really is the best tape. Yeah! I will occasionally interrupt this essay to bring you Script Kiddie Corner, wherein I'll deliver the nerdiest, stankiest comp sci tangents for all you nasty code monkeys. One sec. If you aren't hep to the latest cyber jazz, don't worry, none of this actually matters for the rest of the video. Also, I'm really mixing slang modalities here. Don't worry, nothing I say in Script Kiddie Corner is important for the rest of the video. The program that I wrote for this calculator is mostly function-oriented with a few classes and objects scattered in there. I studied computer programming in the early 2010s, which I gather is like towards the end of the heyday of the whole object-oriented programming craze. I was taught in school to rely on functional programming, so that just comes a little bit more naturally to me. Also, the Arduino IDE is mostly C++, or C++ minus, since I guess the whole standard library isn't in there. Anyways, I'm just a script kiddie. I don't have a core programming philosophy. I think pure functional programming is kind of silly in most contexts, though I recognize it has its uses. I do tend to gravitate more towards the functional end of the spectrum, just because that's what I'm most familiar with. But at the same time, all my college professors would have scoffed at all the global mutable variables and warned me about the dangers of implicit dependencies. But the core organizing philosophy of the main loop is that the state of the calculator changes which functions are called, and any function can change the state to cue future functions in the next iteration. And yeah, that means I need to be careful in every function about which state the calculator may or may not be in. But handling that is cleaner and easier than trying to pass a bunch of biref variables up and down these enormous function chains. So I feel like global variables was the right decision here. But maybe I'm just a sloppy programmer. The mode on the screen right now is called the formula screen. This is where the user enters a formula, a string of 29 characters. It's a 32-character screen, but the last 3 spaces on the screen are reserved for modifiers, like advantage, doubling the dice, or fudging the roll a little bit. The user can enter something like d20 to roll a 20-sided die, or 3d6 to roll in some 3 6-sided dice. It even supports a feature I'm calling bounded dice rolls, where the user can enter something like d3t9 to get a random integer between 3 and 9 inclusive. Once the user enters their 29-character formula, they can hit roll, and the calculator will calculate the results of the dice roll. The process that completes this calculation, how we get from the formula screen to the results screen, is what I want to show you. Here is an example formula, 9d17 plus d20 divided by 2 minus 2 times 5d2. This is a pretty ridiculous formula for D&D, and any tabletop RPG for that matter, but it showcases all of the features that our calculator needs to accommodate, except for the t-operator and modifiers such as double dice or advantage, which we're ignoring for now because those require additional complexity, and I'd like to stick to the basics for this video. Our goal is to parse this formula, calculate the result, and present the result to the user. It's important that the calculator respects the order of operations. Our order of operations is dice rolls first, followed by multiplication, then division, then addition, then subtraction. The characters that appear on the formula screen are stored in the computer's memory in a 29-byte array. That's the 32 characters which can appear on screen, less the last 3 which are reserved for special modifiers. Each of these characters are stored in memory as a number. Anything in a computer's memory is a number. We have a lookup table to tell us which number in memory represents which character. Notice that the number in memory which represents a character may not match the actual value of that character. For example, the 2 character is represented in memory with the number 50, and the 0 character is represented in memory with the number 48. If we fill this grid with the actual numbers that are in the calculator's memory, it would look something like this. You'll notice some zeros on the bottom. Those zeros just mean that that character is blank on screen. We can ignore those for now. Our first step in parsing this formula is going to be converting the string of characters into something that we can do math to. We're going to turn this string of numbers into an array of objects. We'll call them op objects because op object is fun to say. For the record, an array is just a block of memory reserved to store multiple values of a specific data type, in this case, our op object. Each op object is going to be composed of two parts. The first part, represented by this little rectangle on top, is going to be a flag, which tells us whether or not the object is an operator or an operand. An operand is a number, like 7 or whatever, and an operator is a function which acts on operands, such as addition or division or our dice operator. We'll store this flag in memory as a number. Once again, everything in a computer's memory is numbers. We'll use the number 0 to represent an operator and the number 1 to represent an operand. This is only one bit of information, a 0 or a 1, but we're going to allocate a full byte in memory for it because that's the smallest block of memory that we can easily address. The second part of our object is the actual operator or operand that we want to store. For an operand, this is easy. Everything in computer memory is a number, so we'll just store the number that we want. For operators, it's a little more complicated. We'll need another lookup table to specify which numbers in memory represent which operators. For example, multiplication can be represented by the number 3. Notice that I've ordered the operations on this table in ascending order such that the highest order operation has the highest number. This will be useful later. We'll reserve 4 bytes of memory for this part of the op object.
It's time for Script Kitty Corner. If you're a computer-savvy stack wrangler, you might be thinking, hey, I can enter 29 characters and I only need 10 characters to create a number that requires more than 4 bytes to represent. Good catch, I had the same concern. To remedy it, the formula screen doesn't let the user just keep entering operands indefinitely. Eventually, it stops you. And let's face it, if you wanted to try rolling 9,000 random dice, you're better calculating statistical averages than trying to get 9,000 random numbers. So this isn't a huge loss in functionality. Plus, I wanted to make sure that any formula that the user can enter will return a result in a reasonable amount of time without crashing the machine.
Anyways, that's 5 bytes total for the object, 1 for the flag, 4 for the value. In theory, the maximum number of op objects that we'll need to represent the entire formula is 31. That's 29, our formula limit, plus 2 to cover the edge case where the user enters a formula beginning and ending with operators, for which we'll need to addend operands on either side. However, I've allocated space for 64 of these op objects just to be safe. That's a total of 360 bytes of storage, or just over a third a kilobyte. I've got about 200 kilobytes of runtime memory wiggle room in the half mega RAM on this thing, so I've got memory to burn. Let's begin translating the characters from the formula into these op objects and placing them into our op object array. We'll read the formula string from left to right.
57
in memory corresponds to the number 9, so we'll set the op operator flag to operand and store the number 9 in memory. The next item, D, is an operator, so we'll set the flag to operator and give it a value of 4 to represent the dice operation. Continuing on, we've got a 1, so we'll set the flag to operand and give it a value of 1. The next item is also an operand. Whenever we have consecutive operands, instead of adding another operand to the array, we'll multiply the previous operand by 10 and increment it by the new number. So the 1 operand in the array gets multiplied by 10 and incremented by 7 to give us a total operand of 17. Continue this process from left to right. Here's our translated op object array. Now that our formula has been translated into this op object array, it's time to do math to it. When I was first programming the calculator, I'll admit I stumbled on this part a little bit. Whenever I'm confronted with a programming problem that I don't know how to solve, I'll usually begin with the intuitive approach. In this case, the intuitive method is to scan the entire array left to right 6 times, once for each operation in our operation hierarchy, beginning with the highest order operation and stepping down in our operation hierarchy for each scan, conducting the operation whenever we detect it. This way, we preserve the order of operations by ensuring that the highest order ones always get done first. Here's that method in action. We'll start with our highest order operation, the dice roll. We'll scan the array from left to right until we see a dice roll operator. The first one is at the second place in the array. We'll check the op objects to the left and to the right for our operands. We can see there's a 9 to the left and a 17 to the right. This represents 9d17. Our operation is summing 9 random numbers between 1 and 17. We'll conduct this operation and replace all 3 objects in the array with our result. Let me grab my d17s. There we are. Once that's done, we can continue scanning until we find the next dice roll operation at position 3. Check left and right for operands, and we'll see that there is an operator to the left, not an operand. When this happens, that means we should assume that the user intends to roll only 1 dice. That's 1d20. We'll calculate the result and replace both objects in the array just like last time. One moment, please. Then we can continue scanning till the end. There's one more dice operation that we need to calculate and slip into the array. 2, 4, 6, 8.
That is all heads. That's a perfect roll. And now we are ready to move on to the next operation in our hierarchy, multiplication. Multiplication works the same as dice. When we detect a multiplication operator, we check left and right for operands, calculate the result, and replace. Once multiplication is done, we can step down to division, search from left to right. When we have a match, check both sides for our operands. That's 15 divided by 2. We are doing integer division, so the result is 7. Integer division just means we throw out the remainder. Then addition, then finally subtraction. After all of that, there is only a single operand left in the array. This is our result. Yay!
It's time for Script Kitty Corner.
These are going back on.
As an aside to any repo rustlers in the audience, you might be wondering, hey, what happens if I enter an invalid formula? Like, what if the user tries to enter 4 minus plus 5d divided by 0? I mean, that formula sure isn't well formed. I didn't really trust myself to create a sufficiently robust error handling procedure inside of the formula parser. So instead, I tried to program the formula screen so that it wouldn't allow the user to enter an invalid formula. It's not 100% perfect. I missed a few edge cases, for example, if the user only enters minus. But it's not easy for the user to break the system, and in my testing, I've never been able to get the calculator to freeze entirely, so I'm happy with this setup.
Tangent over. As you can see, we've turned that formula into a valid result. If we assume the user entered a well-formed formula, this procedure works pretty well. The best thing about it is just how intuitive it is. It's the exact same process that you were taught in grade school algebra, just with a few dice rolls sprinkled in for some added fun. And there's something to be said for the intuitive approach. Whenever you employ a familiar cognitive model, it's easier to predict outcomes. It helps you avoid mistakes and bugs. Intuitive programming is really helpful when you're coding something that doesn't need to be super efficient, or needs to be easily communicated to others, or something that you need to know is going to work every time. But this is a toy. Worst case scenario, I'm back to rolling physical dice. Damn you, Gary Gygax. I don't need my code to work 100% of the time, and it's okay if I forget how it works in a month. And let's face it, the intuitive system is not very efficient. I have to scan the entire array 6 times. I don't want my code to look like the product of some comp sci undergrad who dropped out after 2 years. I have more self-respect than that. My pride is on the line here. It would be a whole lot faster if the computer could just read the array once. It's easy for people to work like that. We can see the whole thing and focus on the parts that need to get done first. But computers don't think like people. They operate on conditionals and comparisons. A computer can't just look at the formula 3 plus 4 times 2 and see, oh, there's multiplication in there, I should do that first. The computer has to do the whole song and dance I just showed you, where it goes through the entire formula, checking each item to see if it matches the highest order operation 16 times. The computer doesn't even know that there isn't a division until it's gone through to check. The fundamental problem here is our formula notation. The formula notation is the rules for which strings of characters are valid, well-formed formulas, and which strings of characters are nonsense. The formula notation that's most familiar to the user may not be the formula notation that's best for the computer. The style of notation on the formula screen is called infix notation. This is where operands sandwich the operator, like this, 3 plus 4. Just like your grade school math teacher taught you. The addition operator here is in between the 3 and 4 operands. When we use infix notation, there's no way to tell if the operand is supposed to belong to the operator on the left or the operator on the right without checking the operators on both sides to see which has priority. This is why we had to scan the formula so many times. Thankfully, there are other systems of formula notation. Take, for example, this accounting calculator that I stole from an abandoned desk at work. This calculator uses a form of postfix notation, sometimes called reverse Polish notation. Postfix notation looks like this, 3, 4 plus. The operator appears after the operands. To add 3 and 4 in this calculator, I need to type 3, enter, 4 plus. And hey, that's 7. Scrumptious! The nice thing about postfix notation is that it's always read left to right. We don't need an order of operations, we don't need parentheses. So 3 plus 4 times 2 in postfix notation looks like 4, 2 times 3 plus. First operand is 4, second operand is 2, multiply them to get your new first operand. Second operand is 3, add them, easy. The order of operations is just whatever's on the left. We don't need to do any fancy comparisons, we can just read left to right once, and that sounds like exactly what we're looking for. But this raises a new issue. I don't want to force the user to use postfix notation every time they want to enter a formula. I love my accounting calculator, but let's face it, it's a novelty. I love it as a novelty. This is just not a practical tool to me. I'm too used to infix notation. It's how I think. A DM using my dice calculator already has enough to worry about without additionally trying to translate formulas into a notation that they're not familiar with. Nobody who plays D&D is that much of a nerd, right? Right? Why hasn't the camera cut away? And thankfully, someone's already solved that problem for us. We're going to use a method called the shunting yard algorithm. This method is going to require us to allocate a little bit more of our computer's memory to store an additional array, as well as a special stack which we'll call our operator stack. For the record, a stack is a special kind of array where objects are pulled in the reverse order that they're added, sort of like a Pez dispenser. The last one in is the first one out. Here's that unparsed array of op objects again. For the shunting yard algorithm to work, our formula needs 2 operands for every operator. This means that we'll need to insert 1 operands into our op object array whenever there is a D operator with no accompanying operand preceding it. We can do this in that initial translation step, so that's not a huge issue.
Script Kitty Corner. Another tangent for the console cowboys among the audience. Inserting 1 operands in the translation stage before any unaccompanied dice operator increases our theoretical maximum op objects from 29 to 39. If the user enters the formula negative d2 plus 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 d2 plus, there's that for you. 2 operands need to be concatenated to the ends of the formula on either side, and an additional 1 operand needs to be inserted before each dice operator. That's 9 additional operands for the dice plus 2, less 1 because the 22 at the end of the formula there shrinks down into a single operand. But this isn't an issue. As I previously stated, we located space and memory for 64 op objects, and we're nowhere near that, so we're good. We have memory to burn after all.
The shunting yard algorithm works like this. We read left to right. Whenever we see an operand, the operand gets added immediately to the results array. Let's do that and move this 9 operand into the results. Whenever we see an operator, we do one of 2 things. If the stack is empty, or if the operator at the top of the stack has a lower order in the operation hierarchy, then we can push the operator in our formula onto the stack. Let's do that now and push the dice operator onto the top of the stack. Next is a 17 operand. Operands go directly into the results array, so we'll move that there. The next item in our formula array is an addition operator. This is the other scenario. We can only push an operator onto the operator stack if it has a higher priority than the current item on the top. But the current item is a dice operator, which has a higher order than addition. So before we can add addition onto the stack, we'll need to clear the stack. We'll do this by popping all of the items off the stack from top to bottom. Since there's just 1 dice operator, we'll do that now. And look at that, we've already got our first full operation in the results array. 2 operands followed by an operator. Because postfix notation is read left to right, we don't need to wait for additional items to be added to the results array. We can just run this calculation now. In fact, we can guarantee that whenever we add an operator, there will always be at least 2 operands. So whenever we add an operator to our results, we can just run the whole operation immediately. We'll do that now. 9d17 is 85. Now that that's out of the way, our operator stack is clear for our addition operator, so we'll get that moved in there. Up next, the 1 operand can move straight to results. And now we have a D operand. Since dice has a higher order than addition, it can sit on top of addition in our stack, so we'll push it onto the stack. 20 is an operand, so into results it goes. Now we've got a division operator. It can't sit on top of the dice operator, since dice comes first in our hierarchy, so we'll need to empty our stack again. Working top to bottom, we'll pop the dice operator out first for 1d20, which is
Nice.
Then we'll pop the addition operator out to get 85 plus 7, or 92. And this pattern repeats. That's all there is to it. Once we're done reading from the formula array, we can pop any remaining operators off of the operator stack, calculating these operations as we go. 1, 3... I have no idea how to count this. Let's just call it 7. Leaving us with the final result. Huzzah! And that's all there is to it. The shunting yard algorithm lets us calculate as we go. Instead of reading through the formula 6 times, now we only need to read through it twice. Once to translate it, a second time to parse it. We've cut out almost 2/3 of the comparisons that the computer needs to run, and all that it cost us was just a little bit more system memory. And we have memory to burn.
Come on.
A worthy trade, in my humble nerdy opinion. Anyways, that's how my dice calculator calculates dice rolls. Did the shunting yard algorithm make my calculator noticeably faster? No, but I'm pretty confident that the savings wouldn't be noticeable. We're saving milliseconds, probably microseconds. Anyways, there isn't a moral to the story. I just wanted to show you my calculator and explain the shunting yard algorithm because it's cool. So instead of moralizing on you, here's a few animations that my calculator plays. Later!
Boom, 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 boom. Scoopity-dee-bop.
Yes, these are real D17s. I decided I actually did care about bad audio, so I bought a lav mic. Is this what you want, Big Daddy YouTube? Are you proud of me?
Your audio is still horrible. I'm disappointed in you, son. Accept algorithmic punishment.